So I want to provide a quick overview of Brink and what we do. We are a charitable organization whose purpose is to fund Bitcoin and Lightning development specifically. We target as close as possible to the protocol, including Bitcoin and Lightning and some of the supporting libraries that are built on top of Bitcoin and Lightning. We have two different programs that we support. One is our traditional grants program. We take in money from the community. We decide who do we think are the most impactful projects and folks working on different technologies that are going to forward Bitcoin, and we fund those folks. Those are existing developers contributing at a high level. And then we also have a fellowship program, which is a little bit different. Folks that have shown great promise and have maybe started contributing join as a fellow for a year and train under my co-founder, John Newberry, and that's a little bit unique to the industry. So we have a bunch of existing donors. We've been around for just over a year, and we've formed partnerships with a lot of the organizations, all of the organizations here, plus some additional organizations, and so the community has been fairly generous so far. We have, like I said, our grants program, and here's our grant recipients. We have a couple of them here today to present what they're working on, both Jesse and Larry. And so the grants that we're targeting our goal is to have long-term grants. We don't want to fund somebody necessarily just a one-off, a stipend that they use however they'd like. We kind of want to fund them for a year or so at a time. We do have some part-time grants, but our goal is full-time for multi-year. We want those grants to be independent, so whatever the person's working on, they can work on that independently. Brink isn't looking over their shoulder telling them what to do or what to work on. We're there to help and mentor these folks, but not necessarily to guide them. And the goal is to allow contributors to focus on long-time Bitcoin development without worrying about funding. We also have our fellowship program. Gloria and Martin are our fellows, and that is an on-site program that is a year long, and that's in London, in our London office. And my co-founder, John Newberry, longtime core developer, is the mentor, and these folks get to work day to day with them for a year. So this is, like I said, on-site in our London office, and it builds on John's experience mentoring developers over the last several years with the Chain Code Residency, the PR Review Club, etc. And this is really unique in the industry. We want to onboard more developers. Bitcoin's intimidating, Lightning's intimidating, and we use the fellowship as a way to onboard new development capacity. So with that, I'd like to introduce Gloria.
Hello, I'm going to talk very briefly about how Lightning can fail and the very cool work that I get to work on at Brink in order to help resolve that. So can you hear me? Okay. So just to frame the kind of general problem, which is probably familiar to many people, you create a transaction at a relatively low fee rate because you deem that appropriate for getting into the target block that you want to be confirmed by. But then a lot of transactions start trickling in, and it doesn't quite look like you're going to make your target block. So the question is, can we fee bump our transaction? And the answer is not always yes. So right now in Bitcoin, we have two options for fee bumping. One is replace by fee, where you take those same inputs in the original transaction and you create a new replacement transaction with a higher fee rate. And most mempools will have a policy where they will compare the two transactions, see that there's a conflict with their mempool, and accept the new one if it has a significantly higher fee rate. The other option you have is child pays for parent, which takes advantage of the fact that in our mining logic, or in the block assembly logic, it will be somewhat smart and recognize that if a low fee transaction has a very high fee child spending its output, then mining both of them together will allow the miner to collect higher fees. So these are your two options, but they both have limitations. So in RBF, a lot of the logic is designed to protect the node operator from DOS attacks. And this can sometimes make it quite expensive or even impossible for a user to fee bump their transaction in this way. Another problem is that with RBF, it requires you to create a new transaction. So if you are the recipient or you, for some reason, don't have control over all of the inputs, maybe you created this transaction with a untrusted counterparty, if it's Lightning or CoinJoin or some other application, then RBF is not going to be an option for you. On the CPFP side, because we only look at transactions one at a time for our mempool right now, if your parent is so low fee that it doesn't meet the mempool minimum fee rate, then it will be rejected, and the child is thus also not able to be validated. So in periods of very high network volume or transaction volume on the network, your mempool minimum fee might be 5 sats per vbyte, or in the case of late 2017, we even saw 100 sats per vbyte, then you're out of luck. And on the same side, coming back to RBF, we have the same limitation around only validating transactions one at a time, and that means that a transaction's descendants cannot help it be considered as a candidate for replacing mempool transactions. With Lightning, again, I promised I would talk about a concrete Lightning example. We have a combination of conditions that come together to create a very dangerous scenario. The first is that you and your counterparty in your channel negotiate all of your fee rates ahead of time, because the hope is that you never have to broadcast this transaction on chain, but that means that you're going to have to look into the future and consider, okay, what fees am I going to need to confirm this commitment transaction and justice transaction? And you're never going to have perfect knowledge, so you usually end up overshooting. The second is RBF is not an option, especially if your counterparty is trying to cheat you. You're not going to get them to sign a new transaction with you. And the third is that you're usually constrained by a time lock. So I like to use L2 because it's simpler than L and penalty. So for example, in L2, your counterparty might broadcast an old state as an update transaction, and you have until the relative time lock expires for them to be able to broadcast their settlement transaction to add a update transaction that comes as a later state. And you're saying, no, they broadcast an old state, here is the actual balance between us on the channel. But if that relative time lock expires, and for some reason you weren't able to get your transaction into the mempool because of high fee rates and blah blah blah, then your counterparty actually gets away with those funds. So this is kind of a dangerous scenario. As a concrete example, right now in LN penalty, you and your counterparty each have your own version of the commitment transaction. And this is intentional because we want to be able to attribute blame and see who was a party that broadcast a transaction on chain. However, because they're going to be the same fee rate, because why wouldn't they be, they aren't able to replace each other. So no matter how high fee the child you broadcast with it is, you're not going to be able to replace it, and most mempools will essentially just accept the first commitment transaction that they see. And this is a problem. So the solution, some of you may have heard of package relay, which is the ability to broadcast and accept packages of transactions on the P2P network rather than just individual transactions. And this removes a limitation. Like I said, it all just boils down to us only looking at transactions one at a time. I like to distinguish package relay, which is a P2P protocol change, from package mempool accept, which is all the mempool validation code as well as the policies that we would use to analyze different packages to see if they're more incentive compatible to submit to our mempool. So what that is going to look like is typically you'll have a package of a low-fee parent and a high-fee child. That's kind of the basic use case that I've kind of described thus far. And package RBF, where that child is also able to pay for replacing the conflicts of the parent. And we combine this with batched fee bumping, and we get lovely guarantees where we're able to use one child to pay for their parents as well as replacing the conflicts of those parents. Now, this obviously might sound very simple, and you're like, why don't we have this in Bitcoin Core already? You've been doing your fellowship for 10 months. Well, one complication or feature, I guess, of Bitcoin is we believe that anyone should be able to send a Bitcoin payment. That's kind of the whole point, is to be censorship resistant, to be permissionless. But that also means that your peer on the P2P network, the Wild West, can be anyone from someone trying to DOS attack your CPU, trying to cause you to have an out-of-memory error, maybe even placing stuff into your mempool that causes you to stall, trying to compute something later down the line. A competitive miner might want to fill everyone's mempools with garbage or stall the network for like even 200 milliseconds in order to get a head start on the next block. And of course, when we're talking about Lightning, there's two counterparties, and we want to design a system where, okay, we play out the scenarios, and hopefully the honest party is always able to fee bump their transaction if it's incentive compatible for miners to include. And of course, there's privacy considerations. So most of the complexity around package mempool accept is around DOS considerations and making sure that we're not massively bloating the complexity of what we might be causing our validation engine to do as a result of a peer on the Wild West of the P2P network sending us something. But even beyond DOS, if we lean too far and we are too conservative about DOS protections, we can also create pinning vectors or censorship attacks. So one example is in the mempool validation code, we will very carefully limit the number of ancestors and descendants that we have on each transaction. And this is because if you have really, really long chains, it's very easy for someone to flush out your mempool and replace, like conflict out half of it, for example. And also, anytime we want to update, if it's a new block or if it's a reorg or we're deleting things, inserting things, we don't want to be iterating and just exhausting our CPU trying to figure out how to update everything in our mempool. However, if when we're looking at packages, this is like very much more complex because there's so many different relationships that you can have between even just two transactions and a mempool of several thousand transactions, of course. And if we use imperfect heuristics, then we can cause pinning attacks. And it's a whole rabbit hole that I won't get into today. Another example is if, for example, we are looking at duplicate packages. So, for example, in regular individual transaction relay, if we see a failed transaction, we probably don't want to validate it again if our peer sends us the same one. And this is very easy because you can just use a WTX ID, for example. But with packages, it's the same idea. We don't want to create a DOS vector where an attacker can just send us the same package over and over again, or the same version, or different versions of the same package over and over again, and get us to just waste our computational resources on these invalid packages. But if we're slightly imperfect in the way that we analyze whether a package is the same thing, or we allow the P2P network to be relaying slightly different versions of the same package over and over again, that not only destroys or it bloats up network bandwidth, but also we could create censorship vectors because attackers can utilize our imperfect logic to censor honest people's packages. Okay, I just got a time warning, so I'm going to stop here and invite Jesse to come up and talk about Frost.
Hi, so I am working on an implementation of a threshold signing system called Frost, which stands for Flexible Round Optimized Schnorr Threshold Signatures. This was a paper based on a paper published last year out of the University of Waterloo and the Zcash Foundation that is a significant advancement over previous Schnorr threshold systems. So before we kind of get into what Frost is and all that, just do a quick background on why we need this. So in some ways, a private key has too much power. It sort of gives you, in many instances, God mode over some coins. And so we have this problem, how do we secure a number that has so much power? And how do we share this power amongst other participants in a way that's private, in a way that's scalable, and in a way that's trustless. So how this has kind of classically been done is with Shamir secret sharing, where we take a key and we can split it into shares. And a threshold of shares is required to reconstruct the key. Now, there's some weaknesses with this, which is that we need a trusted dealer to generate the secret and then split it into the shares, which isn't great. We also, when we bring the key back together, our secrecy is now lost, and the key becomes vulnerable again. So one way around this is to use protocols or scripts that let us require multiple signatures to authorize a transaction. And so we can have this kind of segregated access, joint accounts, lightning channels, escrow, or in an organization if we want to map the authorization onto the organizational hierarchy and the role separation in the organization. We can do this with multi-party signatures. Or even if we're just looking at a single entity in terms of key management, we can have a much more secure system than Shamir, where we don't have a single point of failure, no trusted dealer, and we don't have to reconstruct secrets. So we can do this with a script on chain, where we can just specify, here's the public keys, and this is the threshold of public keys that's required. But this is a privacy loss, because when we go to redeem this script, we have to reveal the setup, which is not ideal. And it's a scalability loss, because we have to now store more data and keep that around that lists all the explicit verification information, all the keys, and so on. What would be better is if we could do this off-chain and just push to the chain a single key, a single signature, which is very private and very scalable. Now, what we have in Bitcoin today in terms of signing is signing algorithms is ECDSA, which was created to get around the Schnorr patent. So it's a little convoluted in its construction. It's nonlinear, and to do threshold protocols, we need really complex protocols that have many, many rounds, new cryptographic assumptions. Whereas with the Schnorr signature, it has a linear form. We can have a simpler protocol, less assumptions. And when Taproot activates, we now have access to this wonderful signature type that enables this whole world of new cryptographic schemes. So you're probably already familiar with MuSig, which is a Schnorr-based multi-signature protocol. And so MuSig is always an n of n structure. So if we have 5 participants, we'd require the signatures of all 5 of them to form the signature, the aggregate signature. Whereas with threshold signatures, we can do a T of n configuration. So we can have like a 3 of 5 or 4 of 8 or whatever T of n we want to construct. Now, one advantage of MuSig is we have non-interactive key generation. So when we set up the key, the parties don't actually have to interact with each other. Whereas with Threshold and Frost, it's more involved it requires a couple rounds to generate the key when you set it up. By the way, my project is to implement Frost in a way that's compatible with the Bitcoin flavor of Schnorr signatures and is built on the Bitcoin SecP cryptography library. So before Frost, we could do Schnorr threshold signatures, but there's a lot of limitations. If you want to do it in the most secure form, that would require all the participants to be online. You can't do it safely with concurrent signatures unless you add more rounds. You can't reduce it. You can't use pre-generated nonces, and so on. And so with Frost, we get unlimited concurrency. We get less rounds, and potentially we might be able to pre-generate the nonces in a way that's secure and reduce the signing down to a single round. So what does this look like? How does it work? So this diagram is if we just look at the left column here, we're basically looking at Shamir secret sharing, where Alice is going to generate a number of random coefficients that is equal to the threshold we're going to set up. So in this case, we're doing a 2 of 3. And then each participant has an index. So in this case, Alice is index 1, Bob is index 2, and Carol is index 3. And so Alice will use each index as an x value, plug it into the polynomial to generate the y value. And the y value is the share. And so she generates a share for herself, a share for Bob, and a share for Carol. Bob does the same thing. Carol does the same thing. And then they each aggregate their shares, and it turns out that aggregate share is a share of the sum of each of their individual secrets, and none of them knows this sum. So now they've created a Shamir setup where there was no trusted dealer and nobody actually knows what the secret is. So before Frost, the way we would do this is what I just described is basically distributed key generation. To get the public key, each participant commits to their secret and sends those commitments, and everybody sums the commitments to derive the public key. That's DKG. So in this case, Alice, Bob, and Carol would use DKG to generate these shares. And then you can do the same thing for nonces, where you can generate nonce shares, but the nonce part is a lot more problematic because you have risks of nonce reuse, and a lot of attack vectors are opened up. So in the Frost scheme, what we're going to do is, instead of using DKG for the nonces, we're going to do something that's very similar to MuSig2, which we're going to have a linear combination of 2 nonces multiplied by a coefficient that binds values based upon the signature, which includes the message and the participants and so on. And this is going to allow us to have unlimited concurrency and do this in a much more secure and safe way than we could do otherwise. And this type of scheme is going to become more and more important as we have more complex off-chain protocols that have many more types of keys, or like, for example, in the Lightning Network, where you have a hotkey that you have to reuse over and over again. And so to actually do that safely, one way to secure that type of setup is with the threshold scheme, whereas with Shamir, that doesn't really play nicely with a hotkey because once we bring the shares back together, then we've lost a lot of the security for the next time we want to sign it. Yeah, so that's all I've got. I've got a work in progress PR up in the secp-zkp repo. I'm welcoming any feedback or review. And we've got Larry up next.
Hello. Oh, my name is Larry Ruane. I'm a part-time Brink grantee. So I hope to go full-time someday. And I wanted to, most of what I do is PR review, but I thought it would be more interesting than just saying I do PR review and then go sit down. I thought I would present a project I started a couple years ago, and that I've some of my Brink time I've used to improve this little project, and thought it might be interesting to present here. And it's something I call a network mining simulator. And there's a link to the repo here. And what does this simulator do? It can produce 1 million blocks in 10 seconds. Okay, so that's actually a higher block rate than many altcoins, believe it or not. So, no, so not really. It's not creating real blocks, it's creating simulated blocks. So what the simulator does is it's a command line program written in Go. It's pretty small. It's like 400 lines of code, so it's very limited there. It's very simple, and I consider it a good tool for learning. And actually, Chain Code Seminar, they're using this as part of their curriculum to bring in new developers and teach them some of these concepts. So it's really for learning and intuition building. So what the level of the simulation is very, very basic. It's just a set of mining nodes, and there's only mining nodes, and each of them is creating blocks, generating blocks according to Poisson distribution, which is like real Bitcoin that we're all familiar with. And then these blocks are relayed across a simulated network, and the network has latency. So each branch of the edge of the network has latency. The network is not fully connected necessarily. So what these nodes do is just like in real Bitcoin. They generate new blocks, and as soon as they generate a new block, they forward it out. Or if they receive a block that is better than the one that they already know about, then they relay that to their peers. So and then there's logic in there to make sure that we don't have like infinite loops of forwarding. So and then just like in the real Bitcoin network, you have this kind of setup generates these temporary chain splits. And I'm not talking about hard forks or soft forks here, but just temporary chain splits due to timing. And then there ends up being these reorgs when mining nodes find out about a better chain, and that creates stale blocks. So this simulator is really to get at that aspect of Bitcoin where we have these small reorgs that happen. They happen today, in real life, and. I said before, this is really mainly for learning, but this could be useful. I'm not really sure, but it could be useful for resisting harmful protocol modifications. There's people that are proposing all the time. We had the block size war right in 2015 through 2017, and that's kind of settled down. But it's possible in the future you could have something like that where people are proposing larger blocks or more complex block validation. That's kind of analogous to slower block propagation if the blocks take a long time to validate. Or there sometimes, I haven't really heard this too much, but if people propose like a shorter block interval, then that will change the dynamics of these these chain splits that I mentioned. So these are some of the results of these bad ideas if they were to be implemented. Higher stale block rate, which represents a loss of security because miners will not make as much revenue and they're not going to be willing to put in as much hash rate. Also, it will encourage the formation of specialized block relay networks. We actually had that a few years ago, but I think it's not being used anymore. But a specialized block relay network is easier to attack. There's also some of these bad ideas can cause greater incentive for geographic centralization. Now, there's always a little bit of a incentive to do that, but if we make certain changes, larger blocks and smaller block interval and things like that increases the incentive for geographical centralization. That's also easier to attack, for especially state level attack. So the simulator runs off of a configuration. It's just a file that has a static set of mining nodes, each of which has a static hash rate. So it's, like I said, it's very simple. And then there's a static network topology, and each network connection has a static network latency. So time is a big thing in this simulator. There's also a block interval parameter, so you can specify. So default is of course 600 seconds like Bitcoin, but you could play with that and change the block interval. So here's a quick example, like a really simple. This took me 5 minutes to think of. It's a simple example of a configuration file for the simulator. There's only 5 miners here, and each row or each line is a mining node. It has the name of the miner, then the hash rate, and then to the right of that are the peers. So this is not a fully connected network, and then with a delay. So for each configuration or each peer has a delay, network delay, and so you run that. It takes about 10. If you ran that configuration, it takes about 10 seconds, and then you can see like a bunch of statistics that prints out a summary at the end. And like one of the most interesting things is probably the stale block rate. So we see like 1% stale blocks with that configuration. And then you can see the per nodes have different stale block rates because depending on where they are in the network. And then you can change the parameters of this. So here I increased couple of the delays, network delays, and then the the stale rate went up, it more than doubled, stale rate here with that change. And then this next one, I decreased the block size to 2 minutes, from 10 minutes to 2 minutes, and then the stale rate went crazy, is a 10% stale rate. So this will show that's very bad for the network. You can also turn on detailed tracing mode -T option on this, and then it'll print a line for everything that happens in the simulator. So you can analyze exactly how the reorgs happen. It's kind of cool to study when those happen. It does print a line too for reorgs. And I have some future improvements, and that's it. That's all I have to cover.
We don't have time for any questions today, but if you're a developer and you're working on open source software, if you're curious about some of the stuff that these guys are talking about, if you're curious about working in open source, come see us. If you're a representative of an agency that can contribute to Bitcoin open source development, also please come talk to us. And thank you for your time.